So please type in the chat box. Am I clearly audible to all of you? Is the audio and video clear? No response. But why? So please type in the chat box. Am I audible? Is the audio and video clear? Good morning. It's audible, right? Good morning, Damendra, Shubhashish, all of you. एक बार आवाज confirm कीजिए. It's audible, right? Yeah, thank God. Fine. So because I was not getting response for some time, so I felt like, you know, audio is not there. Okay, great. So in this lecture, we will conclude our differential analysis, and also we will step into control volume analysis of fluid systems. Okay. So इस वीडियो में हमें बेसिकली ये 3 टॉपिक्स है, मतलब फ्लो विजुअलाइजेशन लाइंस. फ्लो विजुअलाइजेशन करने के लिए हमारे पास थोड़ा टेक्निक्स है, स्ट्रीम लाइंस, पाथ लाइंस एंड आल्सो स्ट्रीक लाइंस, time lines we have again. Okay, so we'll see all this stuff, and we'll also see in case of steady flow how these 3 things are equal and all physically. Okay, and we'll also look at continuity of the continuity equation both in Cartesian and also in cylindrical, and also we will look at certain deformation of fluid elements. Okay, so like how fluid elements will deform in the flow, so we will see that. Then we'll also look at control volumes, some introduction to control volumes, and also we will see at some divergence theorem, which is very important actually. Okay, when we are talking about this Reynolds transport theorem, converting surface integrals to volume integrals, all these things, they involve divergence theorem. We will actually see what is divergence theorem and how it can be applied to various control volumes. Okay, and like as we go, we'll keep on solving numericals at different stages. Okay, so last time I didn't give you any homework actually, so straight away we will slightly discuss about the topics in the previous lecture. Okay, so we decided Eulerian approach is basically the Eulerian, which is the position based approach, is actually the fittest. Okay, for designing or analyzing these flows. Position based approach is what we are doing. And like if you have a flow like this, then you have seen velocity at any location can be function of ui plus vj plus wk actually. Okay, and this acceleration we have seen, if you do a bit of detailed chain rule analysis, purely maths, nothing big mathematical, if you do, we have seen we'll get this operator operating on this vector v bar. Okay, so this is the vector, and we identified this part is local, or it's also called temporal acceleration, and this is called convective acceleration. Okay, so this is called the convective acceleration. We have seen the first term comes into picture because of changing of certain things in with respect to time. Like for example, valve, we have seen some physical cases where you have a pipe or maybe converging nozzle and you have a valve. Okay, so in this case, convective is because the particles will achieve acceleration even though if nothing is changing with respect to time, but since they are getting displaced from one location to another location, then the fluid particles gets accelerated by means of geometry of the flow. So that's what we call convective acceleration. Okay, so we have seen in Cartesian and in polar coordinates, this gradient operator del is dou by dou r e r cap plus 1 by r times dou by dou theta e theta cap plus dou by dou z e z cap actually. Okay, so this is what you have. This is in polar, and in Cartesian this del can be written as dou by dou xi plus dou by j plus dou by dou z k actually. Okay, and I have given you components for acceleration in Cartesian and also in polar coordinates. So after looking at acceleration, basically steady and unsteady flows, we also started looking at certain small important things, some mathematical adjustments actually. Okay, so in today's lecture we will start it with flow visualization and also deformation of fluid elements actually. Okay, so are you all clear with the last class, what we have dealt in the last class? यहाँ तक सबको ठीक है? Fine. So type in the chat box. Yes. Now let us, good morning all of you. Yeah, now in this class let us look at flow visualization. Okay, now if you have a flow how you can actually analyze the flow. Okay, so how you can actually look at the flow. Normally, like any other technique, you will have two techniques. One is mathematical techniques, using certain principles we will do something, and experimental techniques. Okay, so first we'll see what are this. Which one you want me to say first, experimental or mathematical? both log maths se dagate hai na, so we can go for experimental first or maths, anything is fine. Come on, tell me. Maths, good, fine, okay, we'll see mathematical techniques, then we'll go for experimental techniques. Okay, mathematical, okay, I understand. So first we'll see the mathematical techniques, then also we'll see, put some small analyzation on experimental techniques. Now मैथमेटिकल टेक्निक्स देखने के लिए मैं आपसे कुछ पूछना चाहता हूं. लेट अस सपोज इफ दिस इज XYZ कोऑर्डिनेट सिस्टम, एंड for the simplicity, first of all let me take XY coordinate system so that you can understand better. If I take XY coordinate system, if you have a small curve of length DL, let us suppose this is some small curve, then what I can do is, to study about this curve, I can resolve this into two parts actually, dx and dy, and for small elemental change, you know, this curve will be same as the straight line. Means if you take this curve to be a straight line, whatever the understanding you get, the results will not change much in actual case, because for a small gap, if I draw a straight line with this, look, if I connect these 2 points with straight line, then you won't see much difference actually. These two will be very small actually here. Okay, sir, where is Kamaluddin? Acha, Kamaluddin, yeah, long back I have heard about you. Good. Okay, so dx, dy and dl. Now tell me one thing. The first technique that we generally do is the streamlines. Streamline. So what is a streamline is, streamlines physically do not exist in the flow. It's a hypothetical concept to understand the flow actually. Okay, so see here, a imaginary curve to which tangent at any location or at any point, you can say, gives velocity of particle at that point, velocity of particle occupying that point, because in a flow you can see every particle will occupy a particular position, so occupying that point. So like for example, and clearly you can see streamline is instantaneous, means whatever the curve, इंस्टैंटेनियस मीन्स जो कर्व आपने जनरेट किया था वो कर्व सिर्फ एक ही टाइम पे वैलिड होता है. ओके, सो यू कैन सी लाइक let us suppose if this is the streamline. Okay, so at some time t is equal to 5 seconds or 2 seconds, we have seen a streamline. So at time t equal to t, let us say in generalized sense, you can see at this point, if I draw tangent, okay, so if I draw a tangent at this point, you can see clearly it's a tangent. Okay, so it's a tangent at this point p, for example, then the tangent to this curve will actually give the velocity vector of this particular point. Okay, so this is what you have. Now tell me one thing mathematically, if dl, or let us say ds in general, some direction, a random direction s, can I say ds as, because it has a projection of dx and dy, can I say this dxi plus dyj? Can I say this? Is this clear? Normally, you know, if force is like this, if fx and fy are the projections, we'll say fxi cap plus fyj cap. Similarly, velocity is the vector. If u is the projection on x and v is the projection on y, you write ui plus vj. Similarly, for this ds curve, if dx and dy are the projections, can I say ds is written as dxi plus dyj? Can I write this? Yes or no? Type in the chat box. Same thing, projections. Okay, yes or no? Is this clear to all of you? Yeah. Now if this is the case, the streamline here is along this yellow line, so we can say ds bar is the small elemental length we have taken along the streamline. Okay, so along that streamline we have taken small ds bar actually. Okay, so if this is ds bar, now tell me one thing, at this point if you are trying to find out the relation between this v and ds mathematically, physically, you know, this is nothing but the tangent to v. So mathematically, if you try to calculate this thing, you try to understand v bar comma ds bar are almost coincidental, yes or no? Because at a particular point, the tangent and the curve will lie very close to each other. Okay, they are almost like parallel, so they are almost coincident. Then, if they are coincident, can anyone tell me what could be this cross product of the two vectors? What is the value of cross product of two vectors? Look, this is ds, something like this, and your v is actually something like this. Okay, so this is v and this is ds bar. Then, can anyone tell me what should be the cross product of these two vectors if the angle between them is very close to 0? Yeah, it should be 0, right? Cross product has to be 0. You all know it. If two vectors are parallel or if they are very coincidental, then the cross product is 0. And you know how to calculate cross product. Let us suppose if you are doing in Cartesian, I, j, k, u, v, w, dx, dy, dz is what you have, and this should be equal to 0 bar. Now, if you see I bar times of v dz minus w dy minus j cap of u dz, you all know how to calculate the cross product of the vectors. I'm not again going for that. So plus k cap times of u dy minus v dx. So these guys are going to be 0 bar. Now you know if two vectors are equal, then definitely their components must be same, correct? Matlab I component of this should be same as I component of this, j component of this should be same as j component of this, of course with a plus minus sign. Then k component of this should be equal to k component of this. But in this vector, all three components are zeros, correct? X component, y component, z component, all these are zeros. So from here, what you can understand, we can see v dz minus w dy is equal to 0, u dz minus w dx is equal to 0, and u dy minus v dx is equal to 0 actually. Okay, so this is what you have. He was your favorite student, lots of time. Yeah, I know. Okay, yeah, fine. Okay, good. It's a long comment actually, so to study it took some time. Thank you. So now if you see this, v dz is equal to w dy, or can you understand like this? If I write directly, let us suppose if I send this second term to the right hand side, I'll have dz by dy is equal to dz, v dz minus w dy is equal to 0. So if you send here, we have dz is equal to w by v. From this equation, dz by dx is equal to w by u, and from this equation, dy by dx is equal to v by u is what you have. Now you can understand one thing. See, dz by dy is w by u, and dz by dx is w by u, and dy by dx is v by u. If you write all these three equations in a single form, can you get, let us suppose for example, if I make this conversion, if I pull this w here and if I send this dy here, similarly if I pull this w here and send the dx here, similarly if I pull this dx here and v here, you can understand dx by u is equal to dy by v from one of the equations, and dy by v is in turn equal to dz by w actually. Okay, so this is the equation which we'll solve for getting the streamline, and this is the differential equation for streamline actually. Okay, so if you normally in case of two-dimensional flows, you take any one of these three equations and you will try to solve that. That's it. Okay, and this is instantaneous. So if there is some t in the velocity profile, like for example, let us say u is equal to, if I give you x square t I plus maybe some y to yx j, for example, let us suppose if I give you, if you want to calculate streamline, dy by dx is equal to v by u, so yx by x square t. Now how you will solve this equation actually, because you can clearly understand there is only two differentials, but there are three variables here, y, x and t. But streamline is instantaneous. This is instantaneous concept, because why it's instantaneous? This curve is valid only at this particular situation. After some time, this p may not have the same velocity, yes or no? Because if there is some unsteadiness in the flow, then this point need not maintain this same velocity v with the time. Okay, it can change. If tangent is changing, then definitely the curve for the tangent will also change with time. Okay, so that's why streamline is actually an instantaneous concept. It is valid only at one particular time. Okay, at a particular instant actually. Now let us suppose if I'm asking you this equation at t is equal to 1 second, for example, then what you'll put? You will put t equal to 1 and you will do the integration. That's it. Clear? Did you all understand how did we generate this equation? Okay, if there is involvement of time, we will see at which particular instant we have to calculate the streamline equation. We'll put that particular value of t in this equation and we can generate these two differential equations we can solve. Okay. So is that clear to all of you? Fine. Now let us go to something called path line. We'll see. The path, the actual path traced by a particle in a flow. Traced by a particle in a flow. In a flow actually. Okay. Now let us see, like, you know, if there is a particle, for example, and this is flowing. So let us suppose this can actually go like this. One important point I would like to say here at this point is streamline can never intersect with another streamline. Streamline can never intersect with another streamline or with itself, like you can see. Let us suppose why it cannot intersect with different streamline or itself. Let us suppose if a streamline is meeting like this, okay, or maybe two streamlines are meeting like this. Then what you can understand is, look, at this point, if you try to draw the tangent, at this particular point, if you try to draw the tangent for this bottom part of the curve, the tangent could be something like this, yes or no? And at the same point, if you, when it's going in the reverse direction, the tangent is actually like this, okay. Similarly here, at this point P, the tangent to one curve is like this, so the velocity is in this direction, the tangent to this is in this direction. So this configuration gives you two velocities at a point, but physically in a flow at a point, how many particles can stay? This is mathematically giving you, at this point there are two tangents, means this point has two velocities, but in practice in a flow at a particular point, physically how many particles can be there? How many particles can be there? Only one particle, correct? Because only one particle can be present at a particular location. So if only one particle can present at a particular location, this equation tells you that a particle can have two velocities at the same time. Is that possible? Can a body have two different velocities at a same given time? It's not possible, correct? So that's why you cannot actually input intersection of streamlines, or you can never see two streamlines getting intersected actually, okay, fine. So this yields a single particle having two velocities at the same instant. Having two velocities at the same instant actually here, okay. So at a same instant, two, which is not physically appreciable. Now coming to the path line, so the actual path traced by a particle in a flow, path line can intersect itself. Path line can intersect itself because path, again, the particle may come to the same location again, okay. So this can happen. Now if you see how to calculate path line, if you have, for example, if I take a 2D flow, simply Vj, you know u is nothing but dx by dt, which is equal to u, and dy by dt, which is equal to v actually, okay. Now what we'll do, we'll solve one of the equation from these two, solve one of the equation and replace x or y in terms of t, in second, and solve. Guys, I want to tell you one thing. In few books, which I don't want to mention the names right now, you will see they'll tell you dx by dt is equal to u, and dy by dt is equal to v. So what they write is dt is equal to u by dx, no, dx by u, dt is equal to dx by u, and dt from this equation is dy by v, and they'll tell you this is dt, this is dt, so this dx by u is same as dy by v. So this is the equation of the path line. This is actually wrong. Okay, you can do this only if the flow is steady. Okay, so this is valid only for steady flows. Only for steady flow. I'll ask you one thing. If this is the equation of the path line, dy by dx is equal to v by u is what you'll say, same as the streamline. Now, if I ask you, out of these two terms, let us suppose in one of the components you have time t. Let us suppose if there is some unsteadiness, okay, then, and you don't know, because path line is actually over some period of time, not like instant, okay. Then if you have time in one of these two terms or maybe in both terms, then how do you integrate this equation? Can you integrate this equation? There is nothing with respect to time differential, but still time is existing in the components. Then can you differentiate this? Or can you integrate and basically can you solve this equation? Can you solve? Naina? We cannot solve actually. Yes, we cannot solve this equation if there is time in this. Okay, so that's why this is valid only for steady state analysis. The actual analysis is this. Okay, I have taken a very simple example to show you how to calculate the path line equations. Look, we'll solve this equation. The velocity components of a particle in the flow field are defined by u is equal to 3 meters per second and v is equal to 60 meters per second, where t is in seconds. If the particle is released from the origin at t equal to 0 seconds, the path line equation is given by x square is equal to ky, the value of k is dash. Okay, so you can see they're telling you this particle is actually following this path, then what is the value of k? Okay, so let us see. V is equal to ui plus vj, you know, u is 3 meters per second and v is 60 meters per second, okay, where t is in seconds. If the particle is released from the origin at t is equal to 0 seconds, the path line equation is, see here, you know, dx by dt they have given you as 3, dy by dt they have given you as 60 actually, okay, so this is 60. Now try to understand this thing. First of all, let us solve this equation because it looks simple, or else you can solve this also, anything is fine. So here you can see there is unsteadiness in the flow, okay, so dy by dt or dy is equal to 6t dt, okay, so this is what we have. Now you can integrate this. At time t is equal to 0, the particle is released from the origin. Means if it is released, that means what could be the initial velocity? Released means till that point it is held, correct? So till that particular point, if that is held, then when you release it, the particle's velocity should start from 0. Yes? Yes or no? The particle velocity should start from 0. Means one thing is very clear, at t equal to 0, this guy don't have any velocity, okay, which means u is 0 and v is also 0. Now let us solve this differential equation. At time t is equal to 0, the particle is at location y is equal to 0 because it is at origin, okay, and at time t equal to t, let us suppose this is at some location y, for example. So if you integrate this, integration of dy is y within the limit 0 to y, so y is equal to 3t square, that's it, okay, so y is equal to 3t square. Now come here, if you solve this differential equation, dx is equal to 3 dt. Again, if you integrate at t equal to 0, x is equal to 0, and at t equal to t, this is at some location x. If you integrate, x is equal to 3t. So the particle is moving as per this situation, x equal to 3t and y is equal to 3t square, okay. So at a given time t, means if you want to trace the path line, how it comes here is, see here, x, y, at any given time, x is 3 times of t and y is 3t, means x equal to 0 gives you, if you put 0 in both these equations at time, you will get this point, which is actually the given case. At t equal to 1 second, x is equal to 3, y is equal to 3. So this point is at a location 3 comma 3. So at x equal to 2, this is 6. At x equal to 2, this is 12. So 6 comma 12. So the particle is actually going something like this, okay, and you can get these points if I take t equal to 0.1, 0.2, 0.3, 0.4, like if you give small elemental changes, like in your thermodynamics, if you give small elemental changes, you can clearly get a path line, okay. Now the job is how to get this equation, okay. So the equation is given in terms of x and y, so we have to eliminate t from these two equations, okay. So if you want to eliminate, yeah, it's simple, x by t is equal to t from the first equation because x is equal to 3t. Now substitute here, y is equal to 3t square. and the relation between t and x at any point is 3 into x by 3 whole square. So y is equal to 1 by 3 x square is what we have, or x square is equal to 3 times y is the actual path line. Okay, this is a parabolic profile. So x square is equal to 3y, x square is equal to ky is given, so k is 3, nearest integer, so k value is 3. Did you understand how to do? Yes or no? Yes or no? Please type in the chat box. Clear? Look, I want to tell you one thing. Let us suppose here there is y involvement. Okay, let us suppose you have y here. Sometimes it can happen in case of very non-uniform flows. You can have y here. If you have y here, when you are integrating this, you can take y as constant out, because means you can do partial integration. You can take y out because there is a position differential here. Okay, you have a x differential, means with respect to position you have differential of one variable, so you can integrate y partially. But here to do this, but here if you want to solve this, you don't have any time differential here to take time as partial derivative, partial integral. Okay, so when only position differentials are there, you can take one variable of position constant, one variable you can integrate. But here in this case you don't have any time differential, so you cannot do time differentiation. For the same question, if I give you, if you put this dy by dx is equal to 60 by 3, that's it, you are stuck, nothing to do. Okay, so that's why this is valid only for steady flows. Okay, I'll show you how this is equation of streamline, you can see. Okay, this is equation of streamline. I'll show you in case of steady flow why streamline and path line, both these guys are equal. Okay, I'll show you, just give me some moment, I'll show you. Is this clear to all of you? Yes or no? So please type in the chat box. Is this clear to all of you? How many of you understanding all the things? How many of you feel some good points are coming out? Okay, yes, it's clear, right? Now let's see the next thing, which is take line. This is slightly tricky to understand, but it's very simply explained. See here, the locus of all the particles, that have passed to a particular point, particular fixed point, a particular fixed point. Like, see, for example, let us suppose I have some duct in which some flow is happening. Okay, I'll show you mathematically also, but physically first understand what is a take line. Okay, let me draw a bigger duct so that you can see some things. Okay, now in this duct, let us suppose I have kept some some dye injector. So there is some dye in this, and these particles are coming out. Okay, and the flow is happening like this. Now tell me one thing, whenever these dye particles come out of this injector, these particles will get into the flow, and these particles of dye will flow in the same or basically will flow in the same way as these fluid particles are flowing. Yes or no? Because this dye, if I make the properties very close, that density are almost matchable, viscosity, all these things, if I make approximately the same, then what happens, these particles, the movement of these particles will be same as the movement of these fluid particles. Correct? Yes or no? Can you understand this? Everyone? Dhamendra, Vajit, Kadia, all of you. Okay, so whenever these particles are floating or moving, these particles will move as per the movement of this flow. Now, what I'm telling you is, if you start injecting some small dye particles into the flow, these particles will be taken up by this flow, and let us suppose if the flow particles are moving in this direction, these dye particles will also move in that particular fashion. Okay, so this is what I'm telling you. Now try to understand one thing. Let us suppose this first particle has moved like this. Okay, is moving like this. Whenever the first particle has reached from here to here, the second particle gets out of the injector and let us suppose this second particle moves something like this. When the first particle is here, when the second particle is here, let's assume the third particle might have moved like this. Why they are moving in different things? I mean in different ways, because it's not guaranteed the flow is steady. Okay, so whatever is happening to the first particle means when the first particle is coming out, what is the effect and what's the movement of the particle need not be same as the second particle, right? Because by that time some unsteadiness might have come into the picture and second particle may have taken some different form. Yes or no? Means, can I tell one thing? By the time first particle is here, second particle may be somewhere here. It can be here also, okay, because the effect on this particle may be high. Okay, so the third particle is here. You can see similarly fourth particle is here, fifth particle is here maybe, and sixth particle is here. Then can I say, if you connect all these points, actually, okay, so if you connect all these points, you can understand one thing. The common thing between all these points is all these points in the flow have came out from this particular fixed point, which is the outlet of the injector. Yes or no? The common similarity between all these points which I have connected is actually all these points have come to one fixed point in the flow. Definitely at some time all these points have passed this particular point in the flow. Clear? This is the similarity between all these points. Yes or no? Did you understand? The path what I have drawn in green color is nothing but the point of intersection, I mean the intersection of all the points which have actually come out to this particular point. Okay, yes, I'm repeating, see here. I'm repeating, see. Let us suppose this is the path line of particle 1. This is path line of particle 2. This is of particle 3. Maybe this is coming out like this. So let us suppose if this is P4, P5, P6 like this. So let us suppose if these are the things, then by the time sixth particle is coming out, this first particle might have traveled some distance. Yes or no? By the time this sixth particle is coming out, this second particle might have also traveled some distance from this point. Okay, so by the time this sixth particle is coming exactly out of this injector, these are the positions of the first particle, second particle, third, fourth, fifth and sixth is exactly at this. Okay, now the similarity between these particles is all these 6 particles have come out into the flow to this particular fixed point. Yes or no? So streak line, this is actually streak line. So streak line is locus, or basically the set of all points which actually pass through a fixed point in a flow. The similarity or the common thing between all these points is actually all these particles have come out to this particular point, and all these 6 particles have definitely passed through this point, which is the outlet of the injector at some given time. Yes or no? Is this clear to all of you? Kalyani? Okay, so this is streak line. So this tells you how particles behave with respect to time and how the flow is happening. Means they do not follow each other, but origin is same. Yes, they need not follow. They need not follow each other because there could be some unsteadiness in the flow. Okay, clear? Fine. The location from where they are starting is same, but they need not follow the same path because there could be some unsteadiness. Okay, so path followed by the first particle may not be same as the path followed by the second particle. Okay, now this is streak line. Now how do you calculate streak line actually? Okay, so see, again you have certain velocity profile ui plus vj actually. Okay, then you know dx by dt is equal to u and dy by dt is equal to v. Okay, if you simplify this, you know dx by dt or dx is equal to u dt and streak line is also instantaneous. is also instantaneous. Instantaneous. Okay, so what is the spelling? Sorry. Instantaneous. Okay. Now, why streak line is instantaneous? Because this particular streak line is valid only for this positions of the particles. Yes or no? Let us suppose if this is at t equal to 5 seconds, then at t equal to 6 seconds, what happened? This particle get displaced here, this particle moves somewhere here, this particle moves somewhere here, and if you draw the streak line at t equal to 6 seconds, then definitely you know this t equal to 5 and t equal to 6 will not have the same streak lines. Yes, because these particles will not stay at that positions, they will change. Understood? Is this clear to all of you? Yes or no? Okay, so streak line and streamlines are instantaneous, whereas path line is actually over some period of time. Okay, come on guys, quick. Are you all liking the way that things are going on? Because I know to some of you this is the first time you are talking about streamlines, path lines and streak lines, but I hope all of you are fine with the understanding of the things. Yes? Okay, fine. So let's continue. So normally what you do is, you know, at some time t equal to t naught, definitely the particle would have passed through some location x0, y0. Let us suppose if this point is x0, y0, then at t equal to t naught, the location or the position of this particle is x0. Okay, and at t, this is x. Similarly here you can see t naught and t, this is y, and you know y0 and also y. So you can have an equation in terms of x0, y0, x, y, t, all these things. So at what particular instant you want the streak line, you substitute the value of t, you will get the streak line actually. Okay, so is this clear to all of you? Yes or no? Yes or no? Okay, fine, clear. Now in steady flow what happens? Let us try to understand. In steady flow, streamline is same as path line, is same as streak line. Now let us have a quick understanding why this happens, why this should happen. Okay, now to understand this, let us again take the same thing. You have a channel and you again have an injector. Let us suppose you again have an injector. Okay, then like I have just explained you, let us suppose this is the path line of one particle. Then if this is a steady flow, if this is a steady flow, tell me one thing. Let us suppose at some time first particle came out. Okay, so this first particle came out and this particle has traveled to this path and reached till this point. Okay, now by the time first particle just goes slightly here, immediately second particle will come out. Yes or no? Like see carefully, by the time first particle slightly moves on the path line, immediately second particle will come out. Yes or no? Now since the flow is steady, whatever is the behavior of the first particle, same should be the behavior of the second particle. Okay, so that means if this is the path which is followed by the first particle, then definitely what should be the path followed by second particle which is coming out to the same location? If this is the path followed by the first particle, then definitely since the point is starting from the same location, the second particle is also coming out from the same position and things are not changing with time, then the second particle should also follow the same path. Yes? Is this clear? Yes or no? Can you understand this? Because particles are getting released from the same point and there is no change with respect to time at anything, so they all should actually follow the same path. Correct? Yes or no? Now this is path line of all the particles, path line for all particles. Now if all the particles are following the same path, When first particle is somewhere here, second particle will be here, third particle will be here, fourth is here, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, like this we have the particles. Now, can anyone tell me, if I join all the particles, how this is similar? Because see, if this is a point, let us suppose if this point has this velocity at some time, if the flow is steady, the particle which reaches, the second particle which reaches this location should also have same velocity. Okay, I'm repeating, see here carefully. If this is the path, when a particular particle reaches a point and if it has a velocity v, then the second particle which also reaches this point, if flow is steady, this should also have the same velocity. Okay, means the particles are driven by the same forces, same things and same velocities, and they'll have actually the same path lines. Okay, now can you tell me, if all the particles coming out of this point are lying on this line or on this curve, if I take the locus of all these points, if I start connecting all these points, my streak line will also lie on my path line. Yes or no? Correct? Did you get? Let us suppose on this path line different particles are flowing. Then if I again join all the particles for streak line, for getting streak line, then what happens? This streak line will just get overlapped with this path line. Clear? So can you understand? In a steady flow, path line and streak line are same. Yes or no? Is this clear to all of you? Yes or no? Busy in writing notes? Clear? Yes? Okay. Yes, right? Now, let us see one thing. So, you came to know that path line and streak line are same. Now, coming to streamline. Okay, the same logic what I have just explained you. At this particular situation, if this is the velocity at different points, because this is a, let us suppose if I draw this as a streak line also, you can understand. Actually, I should not plot velocities like this because it's a path line, but let us suppose if this is a streak line and I mean if this is streamline and if I am plotting the velocities, then can anyone tell me, when this particle reaches this position, the velocity of this particle will be same as this vector again. Okay, so at any instant the particles will occupy different positions because they are moving. See, let us suppose if this is at t is equal to 4 seconds, at t equal to 5, this particle may get located here, this particle may get located here, and this particle may get located here. But whatever are the velocities of the previous particles, now these particles which are newly entered that locations, they also maintain the same velocities because the flow is steady. Yes or no? At this point, nothing should change with respect to time. So definitely what happens here, whatever the location or whatever the velocity of the particle which is initially at t equal to 5 seconds, now when a new particle enters here at t equal to 6 seconds, that new particle should also have the same velocity as that of the fifth particle. Yes? So these particles will move, but they move in such a way that the velocities occupied by their previous positions should be same as their particles actually. Means let us suppose if this is the particle which is moving here, then this particle when it's moving here, this particle will take the same velocity as that of its previous particle at that position. Clear? So that's how at any point the tangents remain same. If the tangents has to remain same, the curve has to remain same, which is like this. Clear to all of you? Yes or no? चैट बॉक्स में फटाफट टाइप कीजिए यार, थोड़ा सा लैग हो है, but I understand. So please type in the chat box. Is this understanding clear physically? Why all these three should be same? All clear? Okay. Now definitely since all are equal, the path line equation can be calculated using streamline equation. That's how you can actually eliminate dt. Okay, because there won't be time in the velocities. Understood? Yes? Fine. So this is how we have the all these things equal physically. There is one small concept which is called timeline, which generally is not very much important, but sometimes people ask you. This is a very common thing. This is also instantaneous again. Let us suppose you fix some particles at t equal to 0. Now let us suppose at time t is equal to 5 seconds. This particle will stay there, okay, because of no slip condition. This also stay here because of no slip condition. But since these are close to the boundaries, this particle displaces slightly here, this displaces here, this displaces here, this displaces again here, this displaces here, and there's one more thing. So if you see, this is the movement of the particles, and if you join all these particles, then this is a timeline. Basically, this gives you the movement of the particles with time. That's it. Okay. So this is timeline. So at t equal to maybe 2 seconds. At t equal to 4 seconds, the timeline could be something like this, because the particles will move much. Okay. So that's what you have different things. All these are flow studying techniques, because you can see streamline gives you how the velocities of the particles are changing with time. Pathline actually gives you how fluid particles are traveling with time, and this streak line is also how different particles are behaving with time. So with using all these 3 techniques, and of course this timeline also, using all these 4 techniques, you can actually study how the particles are behaving with time in a fluid flow. Means basically how the flow is happening with respect to time. Okay, so these are the mathematical techniques to calculate flow visualization. Clear? It's almost 40 minutes we have taken, but is the understanding clear to all of you? Okay. Clear? Then let us see one question. Let us solve. Meanwhile, we can have certain understanding. Yeah, this question maybe. So see, okay, fine. Okay, see, a steady incompressible 2D flow through a converging duct with velocity components u is equal to u0 plus bx and v is equal to minus by is flowing. The pressure field is given by P is equal to P0 minus rho by 2 times 2 u0 bx plus b square x square plus y square. Here P0 is the pressure at x is equal to 0. The rate of change of pressure for the given pressure field is dash. Okay, means you can see there is a converging duct. There is a converging duct, and here at any point, at a point x comma y, let us suppose if this is a 2-dimensional case and you take any point x comma y randomly, then what's happening? They have given you velocity u is u0 plus bx and v is equal to minus by. Okay, then the pressure field is given by P is equal to P0 minus rho by 2 times P0 minus rho by 2 times 2 u0 bx, 2 u0 bx plus then b square times x square plus y square, b square times x square plus y square. Okay, so this is the pressure variation with respect to field. Here P0 is the pressure at x equal to 0. Okay, so at x equal to 0, at this location, at all points we have pressure P is equal to P0. Okay, so P is equal to P0 at x is equal to 0. Okay, so P is equal to P0 at x is equal to 0, of course. Okay, so at x equal to 0. Now you can see one thing, the rate of change of pressure for the given pressure field dP by dt, this is the total derivative actually. Okay, so dP by dt is what you have to calculate. Okay, so dP by dt. Then let us see one thing. This pressure is a function of x, y, z, and if you write the total differentiation, we have dou p by dou t plus dou p by dou x into dx by dt plus dou p by dou y into dy by dt is what we have. Okay, so this is dy by dt, and clearly this velocity is v. I mean this component is v, this is u, and in this equation there is no dependence of time, so dou p by dou t is actually 0, because you can clearly see in this equation at any location we don't have any variation with respect to time, so that's t actually. So we get dp by dt is equal to u times dou p by dou x plus v times dou p by dou y actually. Okay, so v times dou p by dou y. Now this expression is in terms of x square and y square. Okay, so let us see u. So what is u actually? u0 plus bx. Okay, so this is u0 plus bx into dou p by dou x. So if you differentiate this with respect to x, let us see what you will have. Minus, because p0 is constant, that gets eliminated, minus rho by 2 times of, if you differentiate this with respect to x partially, we have 2 u0 b. Okay, so 2 u0 b, and this will be 2x b square plus y component of velocity, which is minus by times, okay, dou p by dou y. So if you differentiate this with respect to y, this is 0 minus rho by 2 times of, this first term is 0, b square x square is 0, b square y square 2b square y is what we have. Okay, so this is 2b square y. Now if you put the things together, Let us see if you, so this is the equation that you have to just simplify and put the things together, that's it. Okay, so if you put them together, let's see what happened. So minus rho by 2 is multiplication of this. Let us write one more term, y2 hurry up, u0 plus bx into 2 gets cancelled, minus rho u0 b, again 2 gets cancelled, minus, okay, so minus rho x b square. Okay, so these are the things that you have, minus of minus plus by rho by 2, okay, 2 gets cancelled here also, so rho b square, so 2 gets cancelled here, so rho b square y actually. Okay, so rho b square y is what we have. Now you can see total we have 5 terms, I guess, if you aggregate 1, 2 and 4 terms here. Okay, I think some term is getting common. Let us see what is the term which is getting common. Rho u0 minus rho u0 square b, so this is the first term, so minus rho u0 square b. Okay, density is common in both the terms. Let us take density out. So if you take density out, we have minus u0 square b. Okay, so this is what you have, minus u0 square b minus u0 b square x. Okay, so minus u0 b square x, then minus u0 xb square, u0 xb square, minus of minus, plus of this minus again gives you a minus sign, so minus bx into xb square, so b cube x square, and coming to this term, this is b cube y square, that's it. Okay, so this is the equation that you have, this is the term which is actually present here, just bit of calculations, differential, that's it. Okay, so dp by dt gives you, now yeah, what are the options they have given you? They have given you y square minus x square in all the terms. Okay, so if you keep this as y square minus x square, we have rho times minus u0 square b. Okay, so this is the first term. Then from these two terms are actually same. Okay, so minus 2 u0 b square x is this, and minus b times of y square minus x square. So this is actually the dp by dt, the total derivative of pressure with time. Okay, this is normally called the material derivatives and all. We'll see why it's happening normally when we see the continuity equations. Okay, is this clear to all of you? So let us see where we have that option, rho times of minus u0 square b minus 2 u0 b square x minus b times of, I think b cube is there here, right? Yeah, minus b cube times of, oh, this is written as minus, so this is plus. Okay, because you can see y square term should be positive. Yeah, b cube y square minus x square, so plus b cube y square minus x square, so this term is actually correct in this case. Okay, first option is the correct option. Simple pressure field in the nozzle. Okay, so you can see it's a 2-dimensional, so at any given point velocities will change continuously, and time, with respect to time, nothing is changing, so this is a steady flow. Okay, now let us see certain important things like continuity equation and deformation. Okay, the concept of streamlines and streak lines, path lines, all this stuff is clear. Now let's move to continuity equation. So continuity we'll see in both Cartesian and cylindrical coordinates. First let us start with Cartesian. If you see there is a flow happening, then if you want to analyze this flow, you can also get the continuity equation using control volume analysis. I'll show you, but right now you can focus here. Let us suppose if there is a small cube we have taken, okay, small cube of fluid we have taken, like the common case we take every time. Okay, and let's see, you have x, y and z. This is x, this is y, and this is z direction, for example. Okay, and let us suppose the small element has this length dy. It's a simple equation, actually nothing to worry. So this is dx and this is dz actually. Okay, so this is dz. Now let us suppose if this velocity going to this face, okay, so mass is coming in to these 3 faces, for example. Okay, so mass is coming in here and here and also to the back face. Okay, so the mass is coming to the back face actually. Okay, the mass is coming to the back face. Okay, and let us suppose mass is going out to 3 right faces, I mean the right, the top and also the front face. Okay, so mass is coming out. Then let us define the mass flow rate first of all as m dot y in this direction m dot x which is coming in this direction and m dot z which is going in this direction. Okay, now you can understand one thing. If this is m dot y over a gap of dy, this let us call m dot y plus dou by dou y times m dot y into dy. Similarly, this is going to be m dot z plus dou by dou z m dot z dz. Like I have explained you in case of pressure, you remember using Taylor's first order says if something is changing, then the change in this quantity with respect to this dz is given by this expression, which is the first order Taylor series expression. Okay, during when I'm teaching you pressure gradients and all in hydrostatics, I've shown you how these things come. Okay, and if this is m dot x, then this is m dot x plus m dot x, dou by dou x of m dot x into dx. So this is what we have. Now one thing that we are taking here is at this particular point it's a very small element, so the flow direction has a velocity u and it has a velocity u is not in this direction actually, so it has a velocity u, it has a velocity v, and it also has a velocity w in 3 components. Okay, so there is certain velocity vector at that point, so ui plus vj plus wk. Now since this phase is actually very small, you for example name this as o a b c, in actual case this element is nothing but the very large view of this small fluid particles. Okay, small chunk of fluid particles, some small fluid particles. Then you can see I can assume at every point on this plane the velocity is same, which is equal to u actually. Okay, and so is anyone else having lag issues? It's only mine. Lag? Is there any lag? No, I think it's fine. Actually the system is going fine. No lag, right? No, fine as of now. Okay, good. So see here, this is y. Now you can understand one thing. This m dot x, if m dot y for example, if you see, let us suppose in the y direction if the velocity is v for example, then mass is equal to density of the fluid rho v into v is the y component of velocity into this flow area, which is dx multiplied with dz is what we have. Okay, similarly m dot x can be written as rho u dy dz and m dot x z is equal to rho w dx dy actually. Okay, because mass flow rate is equal to rho av, but one thing that you have to understand is carefully before this, I think I might have explained you. Fine, I'll explain you here. Look, let us suppose if you have a pipe. Okay, fine, so let's assume you got a pipe actually in this case. Okay, then if you cut a cross section here, or instead of this let me mark this point. Okay, if you have a cross section like this, then when you have the pipe of such case where and this line is slightly extensible like this, then the cross section, the cut section whatever you have will be like this. Yes or no? So this will be the cut section. If you want to calculate the mass flow to any substance, okay, if you see this is the mass flow to any surface, for example let us suppose if we have a surface and some mass is coming out, how do we actually calculate the velocity is or how do we calculate the mass flow rate is, look, I'll tell you. If you have a small area here, this is a dA and this is the outward normal n cap to that area, and if flow is happening for example in this direction, V average, the small elemental mass which is coming out to this small area is given by dm dot is equal to rho times V average dot dA. Okay, and mass flow rate is actually a scalar and dot product of these two vectors is actually a scalar. Okay, so this is how we have the expression, or this can be written as rho times V average into or modulus of V average. No, first of all we'll split this. This dA cap can be written as dA magnitude of this area into n cap actually. Okay, so this dA bar can be written as magnitude of the area into the unit outward normal vector. Okay, so this is dA times n cap. Now dA is again scalar, so if there is some scalar you can take out of the dot product. So what you have is dm dot is equal to rho times dA into V average dot n cap, and dot product, if you see rho dA V average, magnitude of V average into magnitude of n cap, which is 1 into cos theta. Like for example, let us say this is the velocity at this location, V average, then this angle theta is between them. You know the classic definition of the dot product. Okay, so V dot n, I mean magnitude of V, magnitude of n, cos theta. Then you can understand one thing. This is 1 anyhow. Okay, so this is 1. So if this is 1, I have explained this concept during hydrostatic forces on curved surfaces. Now you have to say rho times magnitude of V average into dA cos theta. So this dA cos theta component is nothing but the component of this dA perpendicular to this axis. Yes or no? Means for example, if this is n cap and if this is the V average, if you are doing V average dot with n cap, this dA cos theta is nothing but projection of this area onto a plane perpendicular to this V average. That means from here you can understand one thing. If you want to write your formula as mass flow rate is equal to rho VA or rho AV, from here you can understand this dA cos theta is nothing but projection of this area onto a plane perpendicular to this velocity axis. That means this V average and dA cos theta. dA cos theta has to be now like this, perpendicular. Okay, so that's why if you are applying this formula, this area and velocity should be perpendicular to each other. Understood? Means if this is the area, velocity should be exactly perpendicular to this, and in this formula you can apply only if area and velocity are perpendicular, otherwise you should go for dot product. Is this clear? Yes or no? This is the elemental mass which is flowing. Means if you want to apply this formula, area and velocity has to be perpendicular to each other. Means you can calculate. If I ask you what is the mass flow rate here, you will say rho into area into rho into velocity into, you will write the area of cross section but not the area of this slant cut section. Yes or no? That's why we generally multiply this velocity with area of cross section. So cross is actually perpendicular to the direction of the velocity. Okay, but not the slant cut area. If you are writing cut area, then velocity you should take in the perpendicular direction. Okay, that's what you have. If area, if you want to keep straight, then velocity you have to take perpendicular. Like for example, if this, you can do this mass flow rate calculation in two ways. Area perpendicular into V average, which is flowing like this, or this can also be same as, if this slant area you call A1 into, if velocity is like this, then the component resolution is V cos theta, so you should take V cos theta. Anything you can use, but you should make sure these two are perpendicular to each other. Okay, now coming to this situation, that's how we can actually generate this, because we are assuming y component of velocity is exactly perpendicular to this face. So y component of velocity into area into density. Okay, now the main important point is this density may change from location to location. Okay, because the flow is need not be incompressible. Okay, so it can change from location to location. Now you can see in this element, because practically this fluid element is of some fixed mass, you can see if you take this small volume whatever you have here, then in that small elemental volume or differential volume whatever you take, you can understand this differential volume should be under mass conservation. Yes or no? Because the mass of the fluid element remains same as it is. So mass coming in minus mass coming out should be equal to 0 actually. Okay, so mass is coming in through three phases, m dot x, m dot y, m dot z, and going out through three phases, m dot x plus dou by dou x m dot x dx minus m dot y plus dou by dou y m dot y dy. Okay, let us suppose there is some compressibility effect also. It need not be in steady state right now. So mass in rate of change of the control volume. Okay, so let us suppose if we take some small control volume, some small differential control volume, then this we can write as minus m dot z plus dou by dou z m dot z dz. So these things, so net coming in minus net going out should be same as the rate of change d by dt of mass of this particular control volume. What will be the mass of this control volume? Rho times dx dy dz is what you can change. Okay, so this is 0 times dx dy dz. And let us suppose with respect to time your volume is like that. Okay, so this dx dy dz product is actually same. Now if you simplify this equation by putting these terms, okay, by putting rho v, rho u and rho w, actually I'm not doing the simplification right now, but it's very simple. You have this complete equation, then in m dot x, m dot y, m dot z, if you replace with these expressions, the final expression what you will get is dou rho by dou t plus dou by dou x of rho times of u plus dou by dou y of rho times of v plus dou by dou z of rho times of w is equal to 0. So this is the equation which you will eventually end up if you just do some simplification. Okay, you need not do anything big, just keep these three terms in this equation and simplify, that's it. Okay, it's pure algebra, mathematical calculations. If you do that, you will finally end up with this equation. Okay, so is this clear to all of you? Yes or no? So type in the chat box, can you understand this part till this point? Okay, now, okay, I hope it's understandable, right? Yes, okay, so is this clear to all of you? Everyone, type in the chat box, is this clear to each and every one of you? Fine? Yes or no? If you have some doubt, please ask me, I'll go forward. Okay, now yeah, clear. So now in this equation, if you do slight expansions or slight adjustments, you can actually write this equation firstly as dou rho by dou t plus this terms can be written as divergence of rho v bar is equal to 0 actually. Okay, so this is actually a continuity equation for any flow. For any flow, steady, unsteady, uniform, non-uniform, whatever the flow you take, this equation is valid. Now you can also understand one more thing from this. Let's, if you expand this three expansions, you have first function into derivative of second function plus second function into derivative of first function plus second function into this plus dou rho by dou y, dou w by dou z plus w times of dou rho by dou z is equal to 0. Now you can understand something here. We can make this term as dou rho by dou t plus u times dou rho by dou x plus v times dou rho by dou y plus w times dou rho by dou z plus from the remaining terms you can see we have dou u by dou x plus dou v by dou y plus dou w by dou z actually. Okay, so this is equal to 0. Okay, now if this is equal to 0, this is same as this equation, because if you expand terms independently and if you expand, this term is nothing but the total derivative, yes or no? So d rho by dt actually, which is the material derivative or the substantial derivative it's called, basically because it's obtained by substantial expressions of this equation. So if this is d rho by dt, then this is the total derivative which is here plus density times this expression is called divergence of v in Cartesian. Okay, we are doing it in Cartesian, is equal to 0. Okay, now sorry, lag. I think only one or two have internet issues. Okay, because the streaming is going fine actually. Okay, so see here, this is what you have. This dO by dt is the material or the total derivative. So this equation is same as this equation. Okay, this dO by dt and here. Now try to understand one thing. In case of steady flows, the change in density with respect to time partially is 0 actually. Okay, so dou rho by dou t is 0. Now in this equation, if dou rho by dou t, if things are changing with respect to time, or if things are not changing with respect to time, only this term is 0, then you cannot take density out. Okay, because I told you things can change with respect to two reasons. One is because of change in time, one is because of change in position. In case of compressible flows, even if this term is 0 because of steady state, these terms dou rho by dou y, dou rho by dou z, these terms need not be zeros. Okay, understood? So is this clear? I'm repeating, steady state will tell you only this term as 0 but not these three terms. Clear? So that's why in this equation you cannot eliminate you cannot take this density out in case of steady flow, because these things can still exist. Okay, so for incompressible flow, if you say for incompressible flow, if the flow is incompressible, means whenever there is a flow, the density variations in the flow are not at all present, maybe with respect to time or with respect to position, then in case of incompressible flow, this total derivative will be 0, because if the flow is actually incompressible like this, from here to here there could not be any density variations. So this dou by dou x, dou by dou y, dou by dou t, and also this dou by dou t, they are actually zeros. So if all these four components are zeros, the total substantial derivative becomes 0 actually. Okay, and if this is the case, then you can see d rho by dt plus rho times of divergence of velocity is equal to 0, and clearly if this term is 0, then you can cancel, you have then divergence of velocity is equal to 0. This rho is in-house scalar, you can cancel this because right hand side is 0. So this equation gives you divergence of velocity field is actually 0 in this case. Okay, so this is how you have the continuity equation, and in this assumption we have never made anything called steady or unsteady, yes or no, because if the flow is incompressible, by default dou by dou t will be 0, yes or no. So therefore this equation is for incompressible flow, it is valid for both steady and also unsteady flows. Okay, so therefore for steady and unsteady incompressible flow, for steady and unsteady incompressible flow, as long as it's incompressible, divergence of velocity has to be 0. Okay, and this is for any flow, and this equation is same as the equation which I have given you, so valid for any flow. The advantage of writing it in vectors, I have told you, this vector equation can be in general applied for Cartesian or polar or spherical, anything depending upon the as how we write this del actually. Okay, and we write the expansions. So is this clear to all of you? Please type in the chat box, is this clear to each and every one of you? I'll have some water, so please type in the chat box meanwhile. Is everything clear to all of you? Okay, did you get this? Did you understand? This equation is valid for both steady and unsteady incompressible flows. Okay, the only thing is splitting, just bit of maths you have to do to understand this. Okay, now let us see this same story in let us see this same in polar coordinates. In polar coordinates. Okay, now in polar coordinates, when you see this, let us see, you have the r theta z system as usual. So let us suppose you have the xy plane, and also the xy and also the z plane actually. Okay, then you can see and so you can you can do this better. Fine. Okay, yeah, I hope it's looking like a circular piece at least to some extent, or no? Can you all feel that there is a small circular slice or cylindrical slice present here? I have very bad drawing skills, but I hope somehow I am convincing you that there is a small cylindrical surface actually at that point. Yes, can you see that? So you can see this radius at any time is r, this is dr, and this is d theta, and this elevation is actually dz. Okay. Now mass will flow in the radial direction like this, and it will come out like this. Similarly, it enters this face and it comes out of this face, and it enters to this bottom face, it comes out to this top face. Okay. So again, if you write m dot r plus dou by dou r m dot r dr, okay, and this is m dot theta, then this is m dot theta plus dou by dou theta m dot theta d theta, and this is m dot z, then we have m dot z plus dou by dou z of m dot z dz. Okay, so these are the things. Now again, if you write the same point, m dot in plus m dot minus m dot out is equal to rate of change in the mass of this small elemental volume, then the final equation, like where m dot r is equal to, so what would be the radial outlet? Okay, so let us suppose at this point the velocity is radial plus e theta plus vz ez cap. Okay, so in a flow at a particular point in a polar flow, basically we have vr er cap plus v theta e theta cap plus vz ez cap. Then you can write this m dot r as rho times vr into, so what is the area perpendicular to radial? This multiplied with dz. Okay, and this value is nothing but r d theta into dz is what you have. Okay, similarly m dot theta rho v theta, and v theta is actually flowing parallel to this face. Okay, then what is this face actually? dz into dr, and m dot z is equal to rho vz into the base. If you take the base, actually this is r times d theta and this is dr, so we have r d theta dr is the base actually. So this is the expression, and in this m dot in, if you write m dot r plus m dot theta plus m dot z minus m dot r plus dou m dot r by dou r into dr minus m dot theta plus dou by dou theta m dot theta d theta minus m dot z plus dou m dot z by dou z dz. This is equal to total rate of change in rho times dr r d theta into dz. So this is the volume. Okay, so again this is the mass balance equation, basically this equation. Now in this equation, if you replace with these three terms where m dot r is this, m dot theta is this, and m dot z is this, and if you do little bit of algebra and simplifications, what you get here is again d rho by dt plus rho times divergence of v is equal to 0 is the equation that you will get in vector form. And here if you see d rho by dt, d rho by dt is actually dou rho by dou t plus vr dou rho by dou r plus v theta by r into dou rho by dou theta. It's gradient, so v dot del, fine, yeah, this. So plus vz times dou rho by dou z is what you have, and divergence in case of polar is, like I have told you, dou vr by dou r plus vr by r plus 1 by r or v theta by 1 by r into dou v theta by dou theta plus dou vz by dou z is equal to 0. This is actually the divergence. Okay, how this one extra term is coming, that we have to go to a bit of mathematics. Conversion of Cartesian to polar, actually in case of divergence will give you that 1 by r. Normally if you have to go for some matrices, and if you do the gradients of vectors and gradient of this del in polar coordinates, you can easily identify that this 1 by r's actually come out here. Okay, this 1 by r's will be basically because of this excess r in this m dot z. Okay, anyway, that we'll see sometime in detailed course, but the simplification finally will actually give you this equation. Okay, the equation remains same in vector form, but these components will be slightly different. Okay, so if the flow is incompressible, if flow is incompressible, then you can see d rho by dt is equal to 0, and this gives you rho times of divergence of velocity is equal to 0, and this gives you divergence of velocity is equal to 0, which you can write it as dou vr by dou r plus vr by r plus 1 by radius times dou v theta by dou theta plus dou vz by dou z is equal to 0 actually. Okay, this is the continuity equation for incompressible flow in polar coordinates. Okay, so is this clear to all of you? So this is for polar. It's completely mathematical. This equation remains same. So conversion of applying del and also total derivative in polar is what you should write carefully. Okay, so is that clear to all of you? Normally I've been teaching this for past 6 years and teaching maths for past almost 7-8 years. So I can actually remember all these things very in a go, because it's very simple. Okay, I'll give you one more expression which could be helpful to you at some points. Maybe if we are you can see curl v in in Cartesian, you know how to calculate curl. Today also we have calculated some way. For this you have er cap by r, e theta cap, ez cap by r, dou by dou r, dou by dou theta, dou by dou z, and we have vr, v theta, r times v theta is what we will have. Yeah, 1 by r, so eta dou by dou eta 2, eta 1, eta 2, eta 3. Fine, so this is cancel. Fine, okay, fine. So you have 1 by r. Okay, so this is actually r v theta and this is vz. This is actually the curl. Okay, so this is the expression for curl in polar. Okay, so taking determinant like how you do for Cartesian, same you have to do. Okay, but this 2 r's and this excess r will come in this picture. Okay, going fast? No, wait, because this is just mathematics. Okay, purely maths, conversion from doctor handwriting. Actually mind में thought process थोड़ा जल्दी चला है. Okay, और जल्दी नहीं, जल्दी is fast ना? Yes, thought process was slightly fast. Normally if you see one thing, there's a saying. Okay, so smart people handwriting is very bad, and generally people who have slightly less knowledge, they generally talk very slow and also write very slow. Because the problem with this smart guys is, when their mind is writing, let us suppose if I am writing this point, I think of this equation actually. Okay, so we want to express that in a very quick way, so talking will be very fast and also writing will be very fast, is what you have. Okay, fine, but anyway I am writing slowly, so not that smart, but still this is the good thing that we see in psychology actually. Fine, anyway, this is the curl of polar, curl in polar actually. And curl in Cartesian is anyhow known to you. Today we have solved one question for calculating curl in Cartesian. That's streamline derivation. Okay, so यहाँ तक सबको clear? So if it's clear, we'll solve one question and we'll see deformation of fluid elements, which is a bit important again for us. So all of you please type in the chat box. Is this clear to all of you till this point? Yes or no? Sorry, clear? Okay, then let us try to understand some things here, some important things here in this case. Yeah, one question we'll solve better, we can understand this. This question is from I have taken from Frank and White again. It's an unsolved question. Okay, so this is one of the good questions, so let us use this. Water enters the bottom of a cone in the figure at a uniformly increasing average velocity v is equal to kt. Okay, if d is very small, they have an analytical formula for the water surface height. For this condition h is equal to 0, at t equal to 0, assume incompressible flow actually. Okay, so like this. All these questions normally in the beginning of the career we have framed almost some 5-6 years down the line, 2018 or 19, I don't remember exactly, but fine. Okay, so see here. Let's solve this. So water enters the bottom of the cone in the figure. Normally this is a question from Frank-White, you can solve. Guys, I'm telling you one thing. Normally majority of the questions what I pick are from two books, Frank-White and also 𝐂𝐚𝐭𝐜𝐡. Yeah. These two are really some nice books for solving questions. Okay, so and many times it's also seen, since this is a YouTube class I cannot open the books and all online, but you can get a soft copy available from sources. You can understand the questions. If you open Frank-White, anybody have a hard copy of Frank-White? If you have, you can see the many questions. If you see the questions which are diagrammatical and all in PYQs, you will see majority of the questions are directly from Frank-White. Okay, this is also one such question. Okay, so anyway, we'll see. So water enters the bottom of a cone in the figure at a uniformly increasing average velocity v is equal to kt. Means this velocity at which the fluid is coming in is increasing with time. If d is very small, so this is d, they have given you diameter d. Okay, so this is the diameter d, which is very small. Initially at height h is equal to 0, t is equal to 0, derive a formula for h of t at this point. Okay, now by looking at this question, definitely some of you can say that one of the answers or two options can be eliminated. Can anyone tell me what are the two options that I can eliminate? What are the two options that I can eliminate? What are the two options I can eliminate? Can anyone tell me? Four options. Can anyone tell me? You can eliminate two options. Can anyone tell me the logic? Guess B and D. Why? What is the problem with B and D? What is the problem with B and D? Why? How can you eliminate? Because I have asked this question just like a fluke. I cannot eliminate any option in this question. Okay, but I just want to see if someone tells you can eliminate. Why? Why you can eliminate? What is the logic? Because I cannot eliminate. Honestly speaking, I have to solve the question and mark the option. Any logic for eliminating B and D? How B and D can be eliminated? Why? What is the logic? Because inside only this constant is changing. Okay, only constant is changing. Nothing else is changing, no? Yeah. So let's solve this question. Guys, see here. Let us suppose if I take this tank as the control volume. Okay. Let's take this tank as the control volume. And let us neglect this small amount of volume because D is very small, they have given. Okay. So let us suppose this is the tank actually. Or let us control that also. Let us take that also here up to this point. Then we'll also draw some more lines. Now this is control volume. Tell me one thing here. Given V is equal to KT. Okay, so V is equal to KT. Now if V is equal to KT, then see here. One thing that you can understand is mass flow coming in minus mass flow coming out is equal to rate of change of mass inside the control volume. Okay, so mass inside the control volume. Now what is, first of all, tell me one thing. In this control volume, is there any mass which is going out? If I make this as my choice of control volume, then mass is coming in and mass is getting stored inside the volume. Is there any mass which is going out of the control volume? Is there any mass which is going out of the control volume actually? Come on, quick. This is a nice question. We can solve quickly and then we'll leave. This is unsolved from Frank-White. So please tell me, this is actually a control volume. Then is there any mass which is going outside the control volume? No, correct? There is no mass which is going outside the control volume. So clearly this term is 0. Okay, so mass out is 0. Now what is mass coming in? Rho into velocity is perpendicular, definitely. So KT into, now what is this area of cross section? This is of diameter small d, so pi by 4 d square. So this is the flow area. So this is equal to d by dt of mass of the control volume. So mass of the control volume can be written as density into volume. So density into volume of the cone 1/3 pi r square h. Now what is this radius? Can anyone tell me what is this radius actually? Exactly at this point, if you neglect this small value h, for example, if you take this as h, okay, so you are neglecting this small channel of diameter and all, then if this is h at any given time, okay, so let us suppose at this time h of t is the value, then if I apply tan theta is approximately r divided by h, so this r can be written as h times of tan theta, okay, and you know clearly as this h increases, this radius also increases, they both increase with respect to this tan theta, okay, so r is equal to h tan theta is what you can say. So r square, which is h square tan square theta into 1/3 pi r square h. Height of the cone at this particular point is h, okay, so this is h, so this is what you have, okay, so 1/3 pi r square h is the thing that you have. Now try to understand something. Because this diameter is very small, I can assume this is closed, okay, for your approximation you have seen this as large, but actually they have given you d is very small. If d is very small, I can assume this is actually closed, okay, so that's why I am taking 1/3 pi r square h. Now let us see what they have told you. Water enters the bottom, so water practically you can take as incompressible fluid, okay, assume incompressible flow is also they have given, so which means this density will remain constant throughout the life, okay, this pi can also be cancelled actually. Now you can see we have, and 3 if you bring here, it is 3 by 4 k d square into t into dt is equal to derivative of 3 has already come here, tan square theta. If you bring tan square theta here, 3k d square by tan square theta into t is equal to d of h cube is what you have, okay, so derivative of h cube is what you have, okay, so this is a variable separable differential equation. Now k is constant, they have given you k, v is equal to kt, so k is some constant actually, so d square t by tan square theta into dt is equal to derivative of h cube. Now to get the height of water level with time, you just have to integrate this. So if you integrate this, can anyone tell me at time t is equal to 0, what is the height h is equal to in this tank? H is equal to 0, they have given you. So at some time t, let us suppose the water level in the tank is h. So if you integrate this expression, you can see 3 by 4 k d square, this 1 by tan square theta we are writing as cot square theta into integration of t is t square by 2, because I am doing definite integration, t square by 2, when you put t square by 2 minus when you put 0 by 2, so this is what you have is equal to. Now can anyone tell me what is this value? Integration of differentiation, this operators get cancelled each other because integration of differentiation gives you the same thing. If you differentiate this, look what you will get. This is h cube within the limits 0 to h, that's it, okay, because whatever is the function here, directly the difference of that function between these two limits, you can understand this, yeah, h cube. For example, if you don't know this point, you can still do one thing, derivative of h cube is 3h square dh, then h is equal to 0 to h, again if you integrate this you will get h cube, okay, so that's what you can do practically. But you can say this integral and differential gets cancelled, so when you put this is h cube directly, okay, because 0 cube is 0. So height at any given time is given by 3, 4 2s are 8, so 3 by 8 k d square cot square theta into t square whole power 1 by 3, that's it, okay. So this is actually the height of the water level at any given point of time, okay. So 3 by 8, so first of all here we have 3 by 8, this is 5 by 8 wrong, then we should not have tan thetas in the numerator, so both are cot square thetas, this is power 2 by 3, so this is also wrong, option A is the correct answer, okay. So this is the simple question, you see hardly 3 steps, 1 2 3, this is just simplification, okay, that's it. But you should know mass flow rates, all these things, okay. So is this clear to all of you? Fine, understandable, okay. 5 symbol, oh my god, okay. I'll tell you one thing guys, see, clear, okay, I'll just spend 1 minute and I'll tell you something important. If you when you are writing gate examination, it's only you who should write the GATE examination. Okay, matlab like your exam should be written only and only by you. Okay, so more than spending time on different things like what's happening in YouTube, what's happening in Telegrams, what's happening in Facebook, what's happening in Instagrams, rather than doing all these things, spend your time for study. Okay, सिर्फ पढ़ने से marks आते हैं. Okay, Instagrams पे, you know, not by trending something or not by doing all these things you can get. Because I'm telling you, GATE examination is being, GATE got started in 1983, the first World Cup of India. Okay, so it's like 17 plus 23, almost 40 years down the line, the GATE examination has started. And you can see one thing, the kind of textbooks that's followed in IITs or at other institutes, they are like saturated almost. Okay, like for example, all these questions, what I'm discussing from right day one, all these questions are from majority from 3 books or 4 books I could say, because yeah, from 4th book also we have taken some questions. One is Frank-M-White, one is 𝐂𝐚𝐿, one is Munson, and the other is 𝐂𝐚𝐿. Okay, so these are the 4 standard textbooks that we are going, we are taking all these problems as of now. Okay, so if you solve all these questions, then definitely it's like you might have encountered majority of the models in the GATE examination. Clear? And if you find some time, if you want some practice, you can start solving unsolved questions of Frank-M-White for fluid mechanics, especially very good. Similarly, in thermodynamics, you can follow 𝐂𝐚𝐿 or also Bogner and Sontag or maybe Mohan and Sapeo. Any of these 3 things can happen. Clear? So any of these 3 books can do good. Similarly, in heat transfer, again, 𝐂𝐚𝐿, Holman, or Incorpore and David is like generally of, you know, some questions are fine, but some questions are of like ESC mains level, like in वो भी बहुत अच्छे बुक है. एंड मैथ्स के लिए जो इंजीनियरिंग मैकेनिक्स सॉरी मैथमेटिक्स बाय BS ग्रेवल बुक होते हैं ना, सो उस बुक से जो क्वेश्चंस गेट के पैटर्न में होते हैं, सो वो क्वेश्चन सॉल्व कर लो, पक्का आपको, यू नो, यू विल ट्राई टू हैव अ चांस ऑफ गेटिंग मेजॉरिटी ऑफ द मार्क्स. सर जी मैं 5th सेम में हूँ, गेट अटेम्प्ट करो या नहीं? बिल्कुल कर लो. आप 3rd ईयर में आए ना, सो डेफिनेटली यू कैन गो. Thought studied for a couple of months, I feel like didn't study anything. No, actually see guys, I'm telling you, in any competitive examination, जो last 3 महीने होते हैं ना एग्जाम से पहले, so वो 3 महीने बहुत इंपॉर्टेंट है. ओके, सो मान लो कि हमारा गेट एग्जाम के लिए नवंबर, दिसंबर एंड जनवरी, ये 3 मंथ्स बहुत इंपॉर्टेंट ही है. ठीक है, सो ये 3 मंथ्स में जो कॉन्सेप्ट्स आप पढ़ते हैं, जो कॉन्सेप्ट्स आप रिवाइज करते हैं, सो प्लीज डू देम thoroughly so that you will have the, like I'm telling you, you solve PYQs completely and also you solve this some unsolved questions here and there, is good enough. And this year, as per the understanding of GATE examination for me over the past, I am teaching GATE for past 7 years, and you know, I have seen few things then and now. One thing that I have observed is, this time if you are getting above 60 marks or maximum 65 marks, you are going to get below 100 rank, pakka. Okay, we'll meet again during the result time somewhere in the online platforms. I am telling you, if you can score above 65, you got settled in the next year, pakka, for PSUs or IITs or IISc at anything. So I have a doubt, is 1500 series necessary? Because I think I should revise. I have lacked in proper revision and new questions might be troublesome. Yeah, you can actually start revising at the same time. Look, for example, I don't say like you subscribe or don't subscribe, it's up to you. But before starting any questions, okay, it's always better to revise concepts of that particular topic and then start the questions. Okay, I think definitely some of you might be giving test series by this time. So if test series are given, then you can see when you start attempting test series, then definitely all your mistakes, conceptual mistakes, calculation mistakes, so you can easily identify at what locations or at what concepts we are actually doing some mistakes. So all these things will get identified because of writing test series. Okay, so test series is one really important thing which all should attempt. So when we should start giving test series? Immediately, I would say, because it's already only 3 months for the exam. लेकिन ना मैं आपको एक चीज़ थोड़ा सा ध्यान से बताता हूँ, आप भी थोड़ा ध्यान से सुनिए. Never, you know, feel something like, मान लो कि एक वीडियो है, okay, so let's assume there's a video like how to get, for example, 85 marks in GATE exam, let us suppose, and in that video 1 or 2 persons or some topper, some all India good rank will be talking about you have to study 8 hours, you should study this subject in this way, all these things they'll do. And many of you have this pressure of, since I did not do all those things, I may not get a good rank in GATE. I am telling you, preparation and strategy is individual for individual people. Okay, like I'm telling you, the same strategy what worked for me in studying may not work for you. Okay, because There could be 100 of reasons for that. Okay, maybe you will grasp the subject best if you go in a different way. I may grasp the subject in a better way if I go in a different way. So never feel like अरे ये इस ऑल इंडिया रैंक 2 बंदे ने, एक ऑल इंडिया रैंक 1 बंदे ने ये बोल की like पहले कॉन्सेप्ट्स पढ़ना है, so उसके बाद प्रॉब्लम्स करना है. So this strategy worked only and only for that person. Okay, it's not like the same strategy should be applicable to all of you. Concepts ठीक से सीखना है, लेकिन प्रिपरेशन कैसे करना है वो इट्स इंडिपेंडेंट. ओके, यू कैन एक्चुअली गो फॉर दैट. क्लियर? सो नेवर फील हेक्टिकनेस और नेवर फील ट्रबलसम लाइक सर गेट में 85 मार्क्स लाने के लिए उन्होंने कुछ स्ट्रैटेजी बताया था लेकिन मैंने कुछ काम भी नहीं किया अभी तक. सो नेवर बी इन दिस काइंड ऑफ fear. Okay, so is this clear to all of you? हर बंदे का प्रिपरेशन स्ट्रैटेजी अलग होता है. ओके, you should somehow figure out what should be your way of studying. That's it. Clear? लेकिन एक चीज क्लैरिटी में मतलब समझ लो, like you should actually finish the topics at the level of gate examination. Okay, it's it's not like I just finished the topic and you know later you are not able to solve gate questions and all. जब आप पढ़ते हैं थोड़ा डेप्थ में पढ़ो बस. Okay, fine. Thank you for listening my pathetic Hindi for past 2 minutes. Let's continue. So this is the question, basically one question, which again it's a nice question. So now deformation of fluid elements. Deformation of fluid elements. Okay, yeah. What is the minimum marks to get into IITs? Sir, 60 marks पर क्या PSU मिल जाएगी IIT? These things we will see after gate examination, because हर साल डायनेमिक्स बहुत अलग होता है. ओके, डायनेमिक्स मतलब जितना PSUs रिक्रूट कर रहे हैं, ओके, जो PSUs में कितना वैकेंसीज है. सो एवरीथिंग विल बी लाइक you know dynamic every year. Okay, so first of all of you try to get at least some 70, try to make your marks above 70. It would be definitely beneficial. Okay, Pakka. Because again number of students with some particular category, all these things change every year, but on an average if you have 70 marks it's like good, it will be a good show. Okay, agar if paper level is same, fine. So let us see the deformation of fluid elements. Now till now what we have focused is the movement of the particles, but we have never worried about the twisting of the particles. Okay, but sometimes fluid layers can get twisted, the particles can get like the fluid volumes can get twisted and all. So we will see how these things can happen. See here, let us suppose there is a flow. For example, we are taking 2D, a 2D flow to understand the things easily. So 2D flow. Now in this 2D flow, let us suppose you pick a element, small element. Now till now what we considered is this fluid particle or this volume of fluid, small volume of fluid is actually moving. Now actually when this particle is moving, definitely if there is a flow, definitely there is some shear stress acting. So because of the shear stress, what happens, this fluid elements can get deformed actually. Okay, so how we actually get the deformations? Like for example in first class I told you tau is proportional to rate of shear strain rate in the xy plane, and this is equal to dou v by dou x plus dou u by dou y. Correct? I have told you this. Now we will see how these things actually come. Okay, so that's the point of interest. Now let us see, if you take that block, I want to discuss 3 cases, but first understand these 3 cases individually. Okay, x, y. Okay, first thing is velocity vector at any point in the flow is ui plus vj. Now I want to discuss 3 cases. 1, u is constant and v is also constant. Okay, so v is also constant, u I plus vj. Okay, and this is the velocity. So we have these 2 components constant. What is the meaning of this? If we take u for example, if it's constant, that means you can see this is x and this is y, for example, origin x, y. Let us say this element is dx and this size is dy. Now, if u is constant, means it's not depending on x or y. Whatever is the velocity of this particle in x direction, same will be the velocity of this particle also in x direction. Same will be the velocity of any particle in the x direction. Yes, can I say this? Yes or no? At any given point, means all these particles will move uniformly in the x direction. Similarly, if y is constant, that tells you that all these particles have unique velocity in the y direction. So every particle will move with a velocity v. A velocity v means, let us suppose, if for example if I take a particle here, if this particle is a, if this particle is getting displaced here, this complete cube without any change in dimensions will get shifted here. Yes or no? Correct? So can you see this cube will without any change, because let us suppose if this particle is having a velocity of 4 meters horizontal and 5 meters vertical, and this point got displaced here. Now, when this particle is moving 4 meters horizontal and 5 meters vertical in a second, definitely this particle will also shift exactly by same amount. Yes or no? Whatever is the y displacement of the first particle, same will be the y displacement of second particle. So definitely what happens? These 2 points should shift horizontally, means this point should shift here and this point should also shift here. There should not be any variation in y coordinate between these 2 points. Similarly, let us suppose if this is the initial gap between these 2 particles, and if these 2 have uniform velocity, that means these 2 particles, this distance will be same between the 2 particles. Means in general, if this u and v are constants, this cube, just if this is the configuration at time t equal to 0, maybe at t equal to 2 seconds, all these particles in this block will occupy a new position. But if you see that length, this total length dx will be same as dx, because whatever is the velocity of this particle, same is the velocity of this particle also, and this total y is same, because whatever is the y component velocity here, same is the y component velocity here. So in a given time, these 2 particles travel by equal amount, so this distance will not change. Yes, so in this case, whenever u is equal to constant and v is equal to constant, the fluid body or the fluid block undergoes pure translation. There is no deformation in this case. Okay, so this is actually a pure translation case, means the particles just shift from one point to another point by equal amount, so that there is no variation. Clear? Is this point clear to all of you? This is actually the case of pure translation when u and v are constants, because every particle gets displaced by equal amounts, so that the net you cannot see anything changing. Is this clear to you? So please type in the chat box. Yes or no? No? Clear? Simple, no? If u is constant, v is constant, that means magnitude of v is also constant. If magnitude of v is constant at any point, that means all these points will travel by equal amount in a given time. Okay, in the same direction, because u and v are constant. So let us suppose if this particle is moving here, this particle will move here, this particle will move here, like this. Okay, now second case I would like to tell you, if u is equal to u of x and v is depending only on y, for example. Okay, so in general you can see this can be function of x comma y, this also can be function of x comma y, but right now we are taking for simple case, for understanding some things, that u is function of x and v is only function of y. Now if you again take the fluid element in a flow, oh sorry, and this is y, origin x, y, this is dx and this is dy. Okay, now try to understand this. If this is dx and if this is dy, whenever u is changing with respect to x, that means, can anyone tell me, if I take 3 particles totally, 1, 2 and 3 here, okay, 1, 2 and 3, if u is changing with respect to x, 1 and 3, if you take the x component of velocities of 1 and 3, is there any variation or will they be same? The x component of velocities between particles 1 and 3, if you take particles 1 and 3, between these two particles, is there any change in x component of velocity or they are same? Is there any x component of velocity change between them or will it be same? The x component of velocity, it depends only on x. It depends only on x. It will vary or it remains same. Let us suppose if u is equal to 3x square is what I have given. Then is u same between these 2 points or will it change between 1 and 3? Same, correct? Because the reason is, if this is the origin, x coordinate is same at these 2 points, so this remains same. Understood? I'm repeating, see carefully, the x coordinate between this point and this point is same, so definitely this u will be same. Understood? But if you take this point 1 and 2, these 2 components will change by some small amount, yes or no? Because there is some difference between x. Like for example, if this is 2, 0, this is 3, 0, then definitely this x coordinate is large, so this can have a higher velocity if that's the function, yes or no? Means one thing I want to tell you, any 2 particles on the same vertical line will have same displacement in the x direction, yes or no? In a given time, let us suppose if this is the configuration at time t is equal to 0, at time t is equal to 5 seconds, if I'm talking about this, what you can understand is, these 2 particles travel by same amount in the x direction, yes or no? Any points on the any particles on the same vertical line will not have any variations in x component of velocity if u is only function of x. Similarly, any 2 components on the same y, okay, so let us suppose if I take 1 and 2, these 2 particles gets displaced by equal amount because these 2 particles are on the same horizontal line. If the particles are same horizontal line, that means the y coordinate of this points is same. Are you know na? Maths mein, if you have this line, how will you write the points? 3, 1, 4, 1, 5, 1, like this, okay? If you have a horizontal line, this y coordinate will not change, okay? Similarly, if you have a vertical line, this 3, 2, 3, 1, 3, -1, 3, -2 like this, then for this vertical line, x coordinate is actually constant, okay? So that's why for any 2 particles on a vertical line, since the x coordinate is same and whenever this function is depending only on x, then this u or x component of velocity for these 2 particles will be same actually, okay? Similarly, for any 2 particles on the horizontal line, y component of velocity is same because for a horizontal line, y is same at any point. If y is same, all these layers or at any particular point or at any particular layer, all these points will have uniform velocity in the y direction. Clear to all of you? Is this points clear? Yes or no? Type in the chat box quickly. Clear? Now, if that's the motion, then in a given time, let us suppose this edge has traveled like this and here. I'm erasing these parts, you might have understood. So in a time t, for example, t is equal to 5 seconds, or if you take some time t, this fluid element will get stretched in x and y directions, okay? But you'll have only linear strains. The reason for this is, see, whenever u is depending on x, the velocity between this particle and this particle will be different in x direction, yes or no? Because x coordinate is different for these 2. Since u is depending on x, the velocities in the horizontal direction for these 2 are different, okay? They travel by same velocity of y, but they travel with different x component of velocities. That means, let us suppose if these 2 particles got shifted to this vertical location, but compared to this particle will move fast, okay? Let us suppose if it's engaging function, then compared to this particle is moving fast. That means this edge, whenever this edge is going here, along by getting displaced by this amount because of these vertical velocities, this element will also get stretched in x direction because this particle is moving faster than this. Yes or no? If this particle is moving faster than this, but still material is present at every point, that means this block is actually getting stretched in this direction because this edge is moving fast. Can you understand why it gets stretched in x direction? Of course, I am taking this as positive function, increasing function. So as x is increasing, velocity is also increasing. That's why it's getting stretched. Okay. If this is a negative function, element will get compressed. Okay. But is this clear? Did you all understand this? Yes. Now, similarly here in y direction also it gets stretched because this particle moves slow in y direction as compared to this particle. This particle actually moves fast because v is actually given by only function of y. Now, if this is the case, now your job is to calculate what is the strains. So let us suppose if this is dx again and this is the excess part in stretching. Okay, so change in length. Change in length. Now, if you write this strain rate, if this is AB, this is A dash, B dash, and let us say for example this is C dash. Okay, then you know the linear strain in the x direction is nothing but B dash C dash divided by this AB, and this is completely happening in a time dt. So 1 by dt. Let us suppose in a small time dt, this is coming from this location to this location. Okay, so this happening in a time dt, for example. This is the configuration at time t is equal to 0, and in a small time dt, this element got stretched to this particular configuration. Okay, so y may be stretch hoga, huh? Yes, it got stretched in y also. Okay, this dy and this dy is not same. Okay, maybe you can see if I call d dash or d, for example, this is d dash. Okay, this is d dash and this is actually your dy. So there is some stretching here. For example, e dash you call this. So this is, oh sorry, this is d dash and this is e. So this is only dy. This part is dy. Okay, but this is due to stretching. Okay, now let us see. This is E dot x because the change in length of this horizontal element is nothing but this B dash C dash. So change in length by original length, and this change in length is happening in a time dt. So this is the strain rate, linear strain rate in x direction. In x direction. Okay, so this is in x direction. Now try to understand one thing. This gap is dx. Let us suppose if the particles on this are traveling at a velocity u, then these particles, because of this change in dx, these particles will travel at a velocity u plus dou u by dou x into dx. Yes or no? Because of this change in length dx, if these particles are moving at velocity u, then definitely these particles will move at this velocity. Yes or no? Clear? Is this point clear to all of you? Please type in the chat box. We'll finish this and we'll close the session, but right now please tell me, if these particles are moving at velocity u, then these particles will move at u plus dou u by dou x into dx. Correct? Because velocity is changing with respect to x actually. Okay, now if that's happening, try to understand one thing. This distance is nothing but u into dt, correct? Because this edge AD got displaced to here, and since these particles are moving with velocity u, then this length is u dt actually. Okay, and what about this length? This length is nothing but u plus dou u by dou x into dx. This is the velocity times dt, gives you the displacement in this case. Okay, so this layer gets displaced by this much distance. Okay, and similarly this AD gets displaced here by an amount of u times dt. Now if you want to calculate this B dash C dash, which is actually the part, what is this total distance right from this y axis to this point? This is dx plus this distance traveled by the right face. Okay, so therefore you can say B dash C dash is equal to, see, this is dx plus the distance traveled with the right face, then this gives you the total distance, okay, from this y axis to this edge, and that's u plus dou u by dou x into dx multiplied with dt. Okay, so this is what you have. Now this is the total distance. From this, if you subtract this part, okay, means from y axis to till this C dash, if you subtract, you will get B dash C dash. Okay, so what is this part? U dt plus dx. So minus u dt minus dx. Okay, so this is what you have to subtract to get this b dash c dash. Simple geometry. Okay, I'm doing just line segment length. Okay, so this b dash c dash is nothing but this total length minus this length. Okay, that's what I have written. So if you simplify this, your b dash c dash is going to be this u dx and dx gets cancelled. This u into dt and this minus u dt gets cancelled again. Okay, so this minus u dt gets cancelled. So b dash c dash is equal to dou u by dou x into dx into dt. So this is b dash c dash actually. If you replace it here, we'll get strain rate in x direction is equal to dou u by dou x dx dt by AB. What is the length of AB? Actually, initial length is dx. This dt is actually here. Okay, this dt is this in the denominator. So if you simplify this, we'll get epsilon dot x is equal to dou u by dou x actually here. Okay, so this is dou u by dou x. So linear strain rate for a given velocity profile will be always dou u by dou x actually in this case. Okay, so similarly, if you write in the y direction, you can find out E dot y will be dou v by dou y is what you will get. The same thing if you do in the y direction. Okay, simple definitions. Linear strain rate is what we have calculated using simple geometry, like using the formula distance is equal to velocity into time. Using this simple things, we can actually get out this E dot y and E dot x from this velocity profiles. Clear? So therefore, in a 3D flow in general, in a 3D flow, you can see in a 3D flow, we can actually write what you can say actually. So for V is equal to Ui plus Vj plus Wk, linear strain rate in x direction is equal to dou u by dou x, in y direction dou v by dou y, in z direction you have dou w by dou z actually. Okay, so this is how we have the strain rates, linear strain rates actually. Okay, so you might have seen these formulas as E dot x, epsilon dot x, epsilon dot y, and also epsilon dot z actually. Okay, so these are the things. Clear? One last thing, can I take just 5 minutes? We'll close the shear strain rates also. Okay, we'll close the shear strain rates part also. So can we do this? Just 5 more minutes. Is this clear first of all to all of you? Okay, this is done. So now let us see the case where u is function of x comma y and v is also function of x comma y. Okay, fine. So you can see origin x, y. Then if you see the deformation in that case, first of all, when u is depending on x comma y, one thing we have to understand is along with stretching, it also get deformed because the y velocity of this point is different and the y velocity of this point is different. Okay, so this edge will actually take this form. Yes. So this edge will actually take some form like this, means it gets stretched and also it rotates slightly. Similarly, this vertical edge also goes like this and maybe the total deformation is something like this. Okay, so this is the total deformation of the fluid element. It gets deformed randomly because of depending on these functions x and y. Now try to understand one thing. This elongation you have seen. So what is this elongation? Just now we have calculated. This is due to, look, this stretching is due to this dependence of u on x, correct? And this length is going to be, if this is dx and this is dy, then dou u by dou x into dx into dt is what you are taking. Okay, so this is the stretch elongation. Similarly, this if you see, this elevation of the surface or basically this flat surface is becoming inclined because of these particles having different y components of velocity, yes or no? So this rotation or this lifting up of the base is happening because these particles have different y components of velocity, and this lifting is basically due to change of y component of velocity with x. So this dimension is nothing but dou v by dou x into dx dt. Okay, right now I'm not doing again mathematics. Okay, I'm not doing some simplifications and all. So can I understand the fluid mechanics from this lecture? Yeah, you can attend Suryadev, no issue. So this is dou v by dou x into dx dt. Similarly here, if you take this stretching, this is due to dou u by dou y into dy dt, and this stretch is nothing but dou v by dou y into dy dt is the stretching actually here. So these are the things that you have. Now if you take this angle as alpha and if you take this as beta, total strain rate, shear strain rate gamma xy is nothing but 1 by dt of total angle of turn is alpha and beta. Okay, because strains are normally, we generally measure them in magnitudes in this particular case. So gamma dot xy, rate of shear strain is nothing but, normally you can see, let us suppose in solid mechanics and all, if you see, if this base is horizontal, you will take only beta as the shear strain. Okay, but here both are deforming, so alpha plus beta and 1 by dt, because this deformation is taking place in a time dt, that's why there is a dot on the top. Okay, now what are these values of alpha and beta? Look, from this triangle, if I take tan alpha, you can clearly see tan alpha is equal to dou v by dou x into dx dt divided by dx plus dou u by dou x into dx dt is what we have. Okay, so you can understand now, this dx gets cancelled in all the terms. We have dou v by dou x into dt. Okay, so dou v by dou x into dt, this term we can write as 1 plus dou u by dou x into dt whole power minus 1. Correct? Can I write this? Because this is in the denominator, so in this denominator 1 plus dou u by dou x into dt whole inverse, and since this value is very small, because dou u by dou x is generally small because we are taking only small elemental change, and dt, the small elemental time is also it's very small actually, differential time, so this term is actually very small in magnitude as compared to 1. Now you know the binomial expansions, you might have seen this, 1 plus x whole power minus 1, the geometric progression 1 minus x plus x square minus x cube and so on for mod x less than 1. Okay, so you have seen this binomial expansion. So in that binomial expansion, if you substitute this value comes out to be tan alpha is equal to dou v by dou x into dt, dou v by dou x into dt. Now this term, if you write this, if x is very small, if you neglect higher order terms here, okay, so if you neglect these higher order terms, this can be approximated as 1 minus x. Okay, so this can be approximated as, so this can be approximated as 1 minus x because of that. So 1 minus dou u by dou x into dt. Now you can understand something here. If you multiply these two terms, tan alpha is dou v by dou x into dt minus dou v by dou x into dou u by dou x into dt. Okay, so this is what you get, and clearly this is a higher order term, again you neglect because there are multiplication of 3 very small quantities, so which is very small as compared to this term. Okay, and clearly you can also guess, if this is very small, then 1 plus x whole inverse will be again very close to 1. So within a small time dt, if this is the rotation, then definitely this rotation would have been small because time is very small. So for small alpha, what you can do, tan alpha can be approximated as alpha. Okay, so in this alpha, what we can substitute is 1 by dt times of, this is the expression for tan alpha, dou v by dou x into dt. So what we can do, since the tan alpha you can replace as alpha for small angles, this is dou v by dou x into dt actually. Okay, this is what you have. Plus similarly, if you do for beta using this triangle, for example, if I call OAB, if you use this triangle, if you do the same analysis using Taylor series first expression and all, I will give you as a homework, you can get it as du by dy dt, and clearly this dt gets cancelled all over and you have dou v by dou x plus dou u by dou y actually here. Okay, that's how you calculate the shear strain rate actually in this fluid elements. Clear to all of you? It is a bit of maths, simple triangle, then making Taylor series approximation, and using this binomial will reduce to -1, and this is what you have. Okay, Fine. So that's how you get this expression gamma dot xy is equal to dou v by dou x plus dou u by dou y. Okay. So in 3D in general, for a 3D flow, you know, v is equal to ui plus vj plus wk. Shear strain rate in xy direction, in xy plane, shear strain rate in xy plane gamma dot xy is equal to dou u by dou y plus dou v by dou x. Similarly in yz, dou w by dou y plus dou v by dou z. Because it's cyclic, you can write if it is u it should be y, if it is v it should be x, and y uv because it's xy here. Okay. And gamma dot xz is equal to dou u by dou z plus dou w by dou x is what we have here. Okay. I'll spend just one more minute and we'll explain something. If you have a cube, for example, okay, so dx, dy, dz, for example, okay. If you have a cube like this, or let's take the dimensions x, y, z, simple, okay. So let us draw a cube and let's take the dimensions x, y, z. It's better. You can, because when it's incompressible, yeah, fine. Okay, x, y, and z. We have one term which is called the volumetric strain rate. Volumetric strain rate or dilatation. It's also called dilatation, which is volumetric strain rate is 1 by dt times change in volume by original volume is what we have. Okay. Now, you know, if you have this fluid element, for example, volume can be calculated as x, y, z, correct? So delta v or dv, let us say, for small changes, you call this dv by v. So if you do dv, you will get xy dz plus xz dy plus yz dx is what you have. Okay, differentiation of three functions, first two into derivative of third plus first and last into derivative of second plus second and third into derivative of first. That's it. Okay. Now if you divide with v all over, dv by v is equal to dx by x plus dy by y plus dz by z actually. Okay. Then if you multiply dt, then you can see dv by v is change in volume by dt. So this is volumetric strain rate. Okay. So volumetric strain rate is equal to dx by x is nothing but change in x direction, which is the linear strain in x direction, by dt. So this is linear strain rate in x direction, linear strain rate in y direction, and linear strain rate in z direction. Okay. So this is in z direction. Now you can understand this epsilon dot v is linear strain rate we have seen, because this particle is getting displaced and, you know, elongated because of some velocity. So dou v by dou y plus dou w by dou z. Okay. So this is actually the dilatation rate. Now can anyone tell me, if the flow is incompressible, what is this dv? If the flow is incompressible, means density is changing. I mean, if density is fixed, then for a given mass, volume should also be fixed. Then what is this dv? For incompressible, flow, what is dv? 0. That's it. Okay. So this is from geometry, from continuity is mathematical. Fine. We have one last part. We'll see the rotations and we'll go to control volumes, RTT, Reynolds transport theorem. Okay. So we'll stop here because we have already crossed some time. Okay. So 15 minutes I think we have extended, but it's okay. As long as you are clear, it's fine. So in today's class, basically we have talked about, this topic I was not able to cover today. We'll deal that in the next session. So some problems we have solved, and in today we have talked about We have talked about streamlines, path, stake, all these things. Stake lines, timelines we have seen, and we have seen why in case of study all these three are equal. In steady flows, then we have seen the continuity equation. Okay, so divergence of velocity is actually 0, and from continuity equation we have also seen the cylindrical coordinates, and then after we have seen the deformations that E dot x is equal to dou E by dou x dou z. Okay, and this is dou E by dou y plus dou V by dou x okay. So these are the things in a nutshell we have seen today. Okay, and thank you, that's it. And if you wish to join, you can get in contact with me at this location. Clear? Okay, fine. Because बहुत सारे लोगों को डाउट्स होता है कि dou E by dou x कैसे आता है. Okay, so streamlines and streak lines and path lines, why they are same in steady flow, all these confusions are there, but I hope this lecture has made all those things clear, and I hope you all enjoyed and liked this session. So thank you all. We'll meet tomorrow at 7:30, and we will see a bit of deformations. For 15 minutes we can talk about deformations, and we'll start control volume analysis and Reynolds transport theorem, RTT. Okay, and after that we'll see Navier-Stokes and flow through pipes, coed flow, plane Poiseuille. We'll see types of flows, simple solutions of Navier-Stokes. Okay, then we'll see one lecture boundary layer, nice concepts, and we'll see turbulent dimensional analysis and also bit of turbo machines I think we can plan. Okay, fine. Then thank you all. We'll meet tomorrow at 7:30. Okay, any questions? Okay then, so fine, we'll meet tomorrow then. Thank you, signing off.